So my name's Scott Collis. I'm from Argonne National Laboratory. I'd like to acknowledge my collaborators, Scott Giangrande, Jonathan Helmus, Dee Wu, Anne Fridlin, Marcus Van Leer Wallaquandi, and Adam Tyson. We're all funded by the ARM Climate Research Facility, which is the United States Department of Energy user facility, very much aimed at understanding the role of clouds, aerosols, and precipitation in climate. The title of my talk is Measuring Rainshafts, Bringing Python to Bear on Remote Sensing Data. This is my second SciPy. I still remember very fondly my first one, which was 2 years ago, coming here, discovering things like IPython and all these utilities I hadn't heard of. It saved me a lot of time on Google. So what's the point of this talk? Well, the science question we're asking, what's the natural scale of precipitation? And can models reproduce this? Precipitation, rain rate at the surface in millimeters per hour, is what we call an observational target for fine-scale models. It's something that we can measure, that we can use to judge the health of a model, whether it's actually accurately representing processes that are important to climate modeling and to weather forecasting. And the role of good software in this case is to join complex domain-specific algorithms together. So we have domain-specific science. We have radar meteorology, which involves its own formats, its own methodologies. But then you've also got mathematical software, mathematical science, minimization, machine learning. So good software bridges the gap between those fields and opens up our data source and our domain to the work that's been done. So basically, what does this really mean? It means getting past data formats and shapes to bring mathematics to bear on real-world problems. The take-home from this, and I've seen this repeated by several other speakers in this session, is that commonly agreed data models is the key to success. Building a good data model, adhering to that data model. I know that the IRIS toolkit does something similar to this. And stuff like GitHub, continuous integration, actually makes the problem tractable in the end, actually allows user-submitted improvements to your software and allows for it to have a life beyond what you originally intended. So first of all, I've got to do a little bit of professorizing because I kind of want everyone to understand what I'm talking about without just dropping terms on here. And I know you guys aren't all radar guys. I'm a radar guy. So radar 101, what does the data look like? Radar stands for radio detection and ranging. Basically, this is a radar without its clothes on. Usually they look like a big golf ball out there because you put a big dome over it to protect it from winds and so forth. Basically, it creates a shaped beam of radiation, usually about 1 degree in beam width, and it pulses it so it has about a 100-meter length in space. And then you send out that pulse at whatever you want to look at, and you gate the return. So by gating the return and timing the time it takes for the beam to get back to you, the radiation to get back to you, that gives you your ranging ability. So a typical range gate in our case is about twice the beam length, which is around about 60 meters. So scanning radars also have the ability to move the antenna or dish in azimuth elevation as well. So in the end, you can map out a volume in space and work out what your scatterers are giving. A typical measurement, which I'll get to in a second, that we measure is something called reflectivity factor. Basically how reflective something is, whether it be a bird, a plane, or in our case, distributed scatterers like raindrops, cloud drops, and ice. There's a ridiculously wide range of binary formats available. Seems to be the way, hey, I'm a new radar company, I'm going to invent my own format. Until recently, it's been very difficult to read without sometimes commercial software. But the good news is there are evolving community standards. Oh, look, I've got equations just to scare everyone. So a little bit more about reflectivity. I want to talk about reflectivity, what it is, to give you a flavor of what we do and why we do this in our software. If you have a distributed points, right, the amount of radiation reflected back at you from a radar beam is simply the sum of the number of elements there and their, what we call their backscatter cross-section. So if I throw radiation at it, how big does it look like to my radar beam? This is both a function of the particle diameter and the wavelength of the radiation. Sorry, I'll use that one, otherwise people can't hear me. The particle diameter and the wavelength which we're using. So typically the radars we use are around 3.1 centimeter in wavelength or 5.4 centimeter in wavelength. When the particle gets to around about the same size or much bigger than the drops we're scattering off, it's no longer what we call Rayleigh scattering. It actually starts scattering off internal structures in the drop, and you basically lose information there. You can no longer get this nice region where the returned power is basically proportional to the number of drops and their diameters, so we can get geophysical insight. Basically, long story short, we take out any information due to the wavelength, and we get this thing called reflectivity factor here, and this is proportional to the sixth moment of what we call the drop size distribution. If you imagine a cubic meter of space containing a certain number of drops, this is the PDF of the drop. So basically the number of drops is a function of their radius. So the take home here is that the thing we measure with the radar is not rainfall, it's not the atmosphere, it's the interaction of the radar beam with the atmosphere. And it's a nasty quantity as well, because a couple of big drops has a much bigger impact than many more smaller drops. So we basically have to actually apply models of what we expect the drop size distribution to be doing to back out things like rainfall rate. And I'm going to talk a little bit about polarimetry as well. A normal radar, you might say, transmit your radiation with the electric field horizontal to the Earth's surface. Polarimetric radar sends out two polarizations, one horizontal to the Earth's surface, one vertical to the Earth's surface. Why is that important? Because this cross-section here can be different in the horizontal as in the vertical. When drops fall, friction at terminal velocity makes the drops go oblate. So they actually have a bigger cross-section in the horizontal than they do in the vertical, so we actually can measure things like the differential reflectivity, or one thing I'm going to introduce soon is the differential phase shift. So why bother? Why is this interesting to radar geeks like me? This is a slice through a storm out of Brisbane from a radar we were using out there during a field program. This slice is taken at 9.1 degrees. This is my reflectivity factor here. We use logarithmic units. This is what we call 60 dBz here. 60 dBz means nasty stuff, basically, either very, very heavy rain or hail. We can see here in the differential reflectivity, we get this big signal here that shows that, yes, there's some anisotropy there. This thing actually has a different cross-section in the vertical as well as the horizontal. When I go to a higher tilt through the storm, so now I'm up at 17.8 degrees, I still have a very high reflectivity factor, but all of a sudden my differential reflectivity has disappeared. These things are scattering equally in the vertical and horizontal cross-section. What this is telling me is I'm actually dealing with tumbling hail now, which on average is actually coming back as spherical, but at 60 dBz these things are scattering a lot. So I introduced the Python radar toolkit 2 years ago when I talked here. I gave a brief introduction to piatt. It was in a very much a formative stage there. I pretty much have talked about the mapping algorithms now. The idea about piatt, it uses a common data model for radial, time range, and antenna pointing, and grid data. The whole idea, the biggest advantage is it has this very nice Babelfish layer. So basically I'll have a whole bunch of different radar formats to read them in. It's all the same command, and they all go into a common data model. So you could have a radar, data coming from a research radar, data coming from a NOAA radar, data coming from Brazil, from all over the place, and it will just look the same. Anything that does an operation on a radar object returns a radar object. So there's no, and the whole way we like to do our contributions is to keep it that way, so as people can put domain-specific knowledge into it, we can very easy rig it in. It's DOE funded, used at the Department of Energy, US academia, and many international collaborators. We have known users in the US, Australia, Thailand, Germany, the Netherlands, France, Canada, Spain, Brazil, and even Cuba. And basically, so you've got your top level class here, and almost all the data is stored in dot fields, and we use dictionaries a lot. We make very, very heavy use of dictionaries. So data will actually be stored in a dictionary along with its metadata at the same time. It's got a whole variety of functions, including very, very simple plotting here. This is actually kind of a long example because I kind of customized the plot a lot. You can pretty much do a plot in one line here. And so here I've plotted out the reflectivity factor. This is from one of our X-band systems in Oklahoma. And this differential phase I was talking about. We also have a bunch of retrieval algorithms and also processing and data quality algorithms, again trying to bring mathematics to bear on our data source. One thing we do, so here is our propagation phase. Well, actually, this is a measured phase difference between the vertical and horizontal channel. As the radiation propagates through droplets in the atmosphere, it changes phase. And it can change phase due to a variety of reasons. One is the liquid water path, but also you can get artifacts due to what we call non-uniform beam filling, when you have part of the beam full of droplets and part of it not, and also due to backscatter phase shifts. So you can get these little spikes in here, and from this signal we want to retrieve just the propagation component. So we wanted to do a conditional fit of a line through this curve to say that the gradient must always be positive. And the way we did that is we used SciPy, the coin linear programming toolkit, which actually, I looked up the website, it was like used to schedule nurses or something like that. It was very interesting. And we do that to do this conditional fit. And the nice thing about this setup is that we can add extra constraints in as we think about them. And so basically, long story short, we get out this nice continually increasing thing. And the thing we're actually interested in is what's called the specific differential phase, which is the first order differential of that signal. And the nice thing about a phase shift is it becomes calibration independent. We don't need to have a very well calibrated receiver because it's a phase shift rather than an absolute value. So that's what we actually use as the predictor of our rainfall rates. So we end up creating a relationship between this specific differential phase in degrees per kilometre and our rainfall rate at the surface. Now, this is one of the things I talked about last time I presented here, so I'll go over it very, very quickly. Radars collect information in azimuth, range and elevation. Climate models and fine-scale models, that your weather guy uses, don't. They work, let's say XYZ, they work in a Cartesian grid. So we want to be able to map from our radial coordinate geometry to a Cartesian geometry. We do a distance-weighted average, so we basically have a sphere of influence. We search for points within that sphere of influence, and we average down. Of course, if you did a straight linear search, where we might have 30,000 points in our radar, and we're mapping to 30,000 points in our grid, that very quickly becomes non-tractable. So, and I know someone else mentioned they used it before, but we use KD trees to do our search, which makes the search order log n rather than n squared. And this very simply is our mapping algorithm here. Invocation of it here, just simply the grid shape, grid ranges here, what I want to grid, and what I want to use as my grid origin. Now, where piatt is different to many other bits of software that's come before it is we treat gate data just as a point cloud. What that means, if I have multiple radars, I can put all of those points into the same point cloud, whether they be moving radars, sitting still, or on an aeroplane, or just stationary scanning radar. So here are the radar files I read in before. I actually call it with a tuple of radars. So if I wanted to just map one radar to a grid, I would just hit it with a single radar. Say I had a network of the NOAA NEXRAD radars, so up in Chicago we have like 3 in our local area. I can actually send multiple radars to that point. So getting back to our science question, this is a rainfall retrieval over Oklahoma where our climate research site is. We have our central facility here, we have a whole bunch of instruments, and we have a network of 3 X-band radars and 1 C-band radar. That's what our X-band radars look like. Again, we've got our golf ball on here, and that actually is the same radar you saw earlier, but with its radome on. And the question we're asking is, are we adequately resolving these Rainshafts? Is this the natural spectral frequency of that structure? So here is a map of a single C-band radar. And again, I'm using the same gridding resolution here. It's all done at about 250 meters. But of course, it naturally varies as you go further away from the radar because the beams diverge. You're not fully resolving that. So, and you can actually see some influence of the scanning pattern on top there. So that's done with, that's a single C-band radar mapped to a grid. And this is what it actually looks like when we map all three of our X-bands in a mesh grid. We can see we're resolving a lot more structure inside that storm. This is a map of the rainfall rate from the C-band radar that we retrieved using the algorithm I showed before. Again, we get this big blob here. Of course, you don't get rain above the freezing level because it's not rain anymore. So we've got this big blob of, what is it, it's about 70 millimeters per hour, and this trailing stratiform region of showers after that big convective core. Here's what it actually looks like from our X-band system. You can see we've got a couple of artifacts where they kind of don't overlap properly, but what we can see is we're actually getting this real nice leaning structure, real nice resolution of where the particulate, the snowflakes are coming down and then actually getting blown around by the wind, creating that rain shaft there. So one of the challenges of using precipitation is coming up with a natural way to compare structures, because like in ARM, we don't care that it gets the rain in the right spot. We care that on average it has the processes right, because rainfall and storms are a stochastic process, and we're only interested in things on average because we look over 100-year timescales. So one way we came up with to describe the rainfall field both in a model but also from this gridded radar data I showed is this morphology technique. And it's really stupidly simple. There are probably much better ways to do this, but this just works very nicely. We take the rainfall field and we set a threshold, let's say 10 millimeters per hour. And then we use ndimage.label to actually count the number of blobs that have a rainfall rate above that. Then what we do is we scan the rainfall rate. And so basically what we end up getting is a plot that looks like this that shows, as a function of rain rate threshold, how many blobs do I have above that certain rain rate threshold, what's the total area above that rain rate threshold, and what's their mean rain rate. So for instance, this is actually from the C-band radar here, from the grid I showed you before. And so we have, we have our peak number of elements at around about 3 or 4 millimeters per hour, just basically big, broad rainfall rates. But when we look at our X-band system, we have a lot more image complexity in there, many, many more points and blobs, and actually out at higher rain rate thresholds. See, the thing about rain rate is if you have an aerial average, it doesn't necessarily sum linearly as well. The area, if you have one heavy rain shaft, it can have more influence on that grid average there. So very briefly, and I'm kind of skipping fast now because I'm trying to cover a lot of material, we can also apply this in time here. This is actually an event that came through. This is that same rain rate, number of points as a function of rain rate, and this shows some very nice temporal continuity here as well. And we can also look at it from a model as well. So this is actually what we observed with our radar, and this is what a model actually showed. And it actually showed a much blobbier, not well-defined rain rate map there. So a couple of take-homes here, things that I did and didn't say during the talk. Well-designed software is a great investment in things like standards and version control and reaps rewards. I showed before that we have, actually, let me go back up here. Where's my little shout out? There we go, that's where it was. So we've got 21 forks now. I'm very happy with that, with piatt. We've had quite a number of unsolicited pull requests to our software, quite a few of them from overseas, and most of them actually not funded by our agency, except for the core work we're doing. It's being used in really unexpected ways. People using it to try to find meteor strikes in radar data, teaching in Thailand, looking at rainfall processes there, and we're very, very happy with that. And things like continuous integration as well has meant that when we get a pull request in, and I'm kind of preaching to the choir here, we can see whether it breaks things. So that's actually allowed us to maintain an operational toolkit at the same time as having as a community-based resource. So that's my email there if anyone has any questions. If anyone ever wants to collaborate or wants lots and lots of data or work with radar data, give me a yell, because we've got more data than we know what to do with, and we have lots of ideas of places we want to go. This is very amenable to student projects as well. Basically, we have a student along, we say, hey, just make us a new module in piatt. So there's the website for the thing and my Twitter tag. Thank you.
Let's thank Scott.